In this segment on semiochemicals, we're going to focus on pheromones, chemical signals that communicate among members of the same species. Pheromones were first discovered in insects, probably in ants for that matter, because they play a prominent role in a whole variety of behaviors of ants, one being how they go about locating food.
Ants, in fact, are little chemical factories. A whole battery of glands produce chemical signals or pheromones that are the commands in ant communication. Ants send messages by laying a trail of these chemicals. And other ants pick them up with their antennae, which are covered in tiny sensory organs capable of reading the complex chemical messages.
So, in this simulation in a laboratory, we have an ant nest and an extract of the ant pheromone from a foraging ant. The foraging ants are the ones that go out and find food, and then they come back to the nest laying a pheromonal trail on their way back to the nest, such that when the other ants emerge from the nest, all they have to do is follow the pheromonal trail rather than go hunting for food on their own. So the extract is being painted right there on the substrate, and it's invisible. You can't see it, so I've put that red line in there so you know where it is. Now watch as the ants start to emerge from the nest. And you can see that they are more or less, with some variability of course, conforming to the pheromonal trail. The person that's done a great deal of research in this area is Edward O. Wilson. And this is a video of him doing this actually in the field.
What I'm doing in this experiment out here in the field with a fire ant colony is putting baits on a blank piece of paper, one next to the colony itself, and then another bait at the end of our little platform of paper, a little distance from the nest, so the ants can't find it right away. I'm going to squeeze the rear end of the abdomen, where the sting is, that contains the trail substance that the ants use to lay down on the ground and guide other fire ants to food and new places for nesting. And I'm going to duplicate this by just taking out some of that material from the rear end of the ant, and then I'm going to lay my own trail and talk to the ants to lead them where I want them to go. And beginning to work, and yes, it's going to work. And now, just a few minutes later, after I laid my trail, the ants themselves are laying their trail on top of that, and the result is a very strong trail, and quite a few ants now are going back and forth, and they'll do that for hours until they collect all that food.
Pheromones. This is an interesting situation. It's pretty unusual, actually. It's a jumping spider that actually mimics an ant pheromone so that it can prey on ant larvae and go undetected, because the ants won't recognize it as a jumping spider because it's mimicking their own pheromone. Here's how that works.
It doesn't matter what you look like, as long as you've got that membership smell. A fact a jumping spider dines out on. It has evolved the ability to mimic the smell of the weaver ant colony it lives with. Then it can roam freely among the ants, picking and choosing juicy meals. The soft, fat larvae are best. A weaver ant confronts what, as far as she's concerned, is one of her sisters. The ant's just doing her job, carrying a larva from one place to another. And here's a sister ant that's bigger and stronger than it ought to be. and doing something it really ought not to be doing. But the smell is kosher, and while there's cause for confusion, there's none for alarm. Despite the occasional counterfeiter, though, smell is overwhelmingly useful to an ant.
So you can see how ants are guided by pheromones. I mean, they can see, but the pheromone is overriding any visual information. Okay, now, dragonfly nymphs, try that again. Dragonfly nymphs, there we go, dragonfly nymphs, like to eat tadpoles. And so it turns out that the tadpole actually will emit a pheromone upon being captured by the predator that will then alert other tadpoles in the vicinity that danger is afoot.
Dragonfly nymphs are more than a match for a poorly streamlined tadpole with a body designed for eating. The tadpole's chances of escape are slim. But only the first tadpoles are easy. Things in this pond are about to change. This tadpole's life is over, but its death will help its siblings to survive. The mangled prey oozes body fluids containing special alarm chemicals. These diffuse through the water to its relatives, activating genes that trigger an extraordinary transformation. Over the next few days, the tadpoles pack on weight and grow large red tails. Remarkably, these large red-tailed tadpoles are the same species as the thinner, brown-tailed variety, but the red tails are the anti-predator version. The larger tail gives them greater acceleration, making them very hard to catch. Their color is more of a mystery. Red may be a warning to predators that these tadpoles are too fast for them. Red-tailed tadpoles take longer to become frogs, but it's better to arrive late than never.
This amazing transformation, or at least I think it's amazing, should bring to mind the example that I used when I was talking about pheromones in another segment of pike that prey upon crucian carp. Now, that was a pheromone, not a pheromone. Why? Because the pheromone was emitted by the pike that then caused a physical transformation in a different species. So, not working within the same species. This example, however, is a pheromone that is emitted by the tadpole that then causes a transformation of conspecifics of the tadpole. So this one is indeed a pheromone and not a pheromone. But it's interesting how they both result in these physical transformations.
What I do as an artist is I take an ordinary object, say a lamppost, and by urinating on it, transform it into something that is uniquely my own.
What?
Mammalian urine is a common container, so to speak, of pheromones that are used for a variety of purposes. And so, oftentimes individual recognition, and this guy's just spraying all over the place. Yes, he's urinating, but he's also leaving a pheromonal trail behind. It's often done in territorial marking, and I think that's what we're actually seeing here with this rhinoceros. And this is a urinary pheromone in mice that actually affects the timing of puberty, to regulate puberty in a way to keep the population size in check. It's a real interesting experiment that was done in North Carolina, in Raleigh, North Carolina, on the beltway that surrounds the city, that has these clover leaves. Okay, so that's the entrances and exits to the thoroughfare. And within each clover leaf, you have grassy areas. Well, each of those areas contains mice. And so the experimenter looked at each of these areas, area 1, area 2, area 3, area 4, each containing their own unique population of mice. And the mice stay within their area. Otherwise, they get squished by cars in the road. So typically, they are contained within their own area and they don't leave that area. So it's a perfect field example. So what he observed, the experimenter, when the population size within any of these areas started to increase, so now there's too many mice relative to the amount of food resources that are available to support those mice, the adult females start to secrete a pheromone in their urine that delays puberty in juvenile females so that they will not become receptive to males. In other words, it's going to limit reproduction. And by limiting reproduction, the population will go down. Now, once the population goes down but then stabilizes in relation to the amount of available resources, then the pheromone is no longer secreted. But of course, when the population size goes back up, it will be secreted once again. There's another interesting use of pheromones. It's for pregnancy blocking pregnancy. It promotes monogamy in mice. This effect is also known as the Bruce effect, named after a researcher who I think was the first person to observe it. So what will happen? We have our first copulation. So this first copulation is going to be the mouse with her mate. Okay. So the female is going to learn his pheromone, his unique pheromone. That's her mate. She's monogamous. When she detects the pheromone contained in urine of other males, what happens is there is a physiological change in her that blocks pregnancy if she were to be inseminated by any of these other male mice. So it prevents her from getting pregnant if inseminated by other male mice. Does not affect anything with regard to her own male because the pregnancy block would kick in after they have already mated. So this is the Bruce effect. Promotes monogamy. And as I said, territorial marking, a very common use of pheromones in males. Here we have a cheetah that is going to check out a tree on its territory and is now going to pee on it as it walks away because urine contains pheromones. It's marking that right there. That's my territory, go away. And it's like us putting a no trespassing sign on our property. I guess we could pee on our property, but somehow I don't think that would work in terms of keeping other humans away. Who knows? Try it sometime. Get back to me on that. Let me know how it works. Okay, here we have a civet. Now, the civet is using cheek glands, not urine, cheek glands to mark its territory. Much like your pet cat does when it does this behavior on you, marking you, the owner, as its territory. So these cheek pouches that contain pheromones, very common in mammals as well. Okay, this is now going to look at a neuronal mechanism, a very interesting one, I think, that affects sexual versus aggressive behavior. That is the vomeronasal organ. Well, I just drew it in. It's inside the nasal passage. Vomeronasal organ, or VNO. In mammals, that is what detects pheromones primarily. I mean, we have some recent evidence that suggests that also the usual scent detectors, the olfactory epithelium higher up in the nose, also plays a role in pheromone detection. But the primary detector is the VNO, the vomeronasal organ. Now that's the brain. And I've drawn the approximate area of a structure in the brain called the hypothalamus, really important structure. And what happens is when a pheromone is detected by receptors in the VNO, which sends projections to the hypothalamus, it then causes the hypothalamus to release a protein called TRP2. And that is what is, as you'll see, going to be involved in regulating aggressive versus sexual behavior. So it's activated by pheromones. Okay, we're going to look at 3 situations here of these rodents. So first we have our resident male over on the right. That's his territory. That's his cage. Now, they introduce an intruder, but the intruder's been castrated. So there's going to be no pheromone released by the intruder, and therefore nothing detected by the VNO, and therefore no TRP2 released in the resident. The resident can see and hear fine. Its usual scent receptors are unaffected, but it's not going to be detecting pheromones via the primary pheromone detector, the VNO. Watch what the resident male does. Nothing. It's ignoring the intruder. It's as if the intruder's not even there. I mean, it's aware that it's there, but it's not behaving aggressively toward it. There is no aggression. Okay, so remember that. That's case 1. Here's the second case. There's our resident male over there. Here's a new intruder, but this guy's been castrated. They then added pheromone to that intruding male. That was done only to regulate the amount of pheromone. Okay, they could have just not castrated it and it would have had pheromone, but of varying levels. This is a highly controlled study. Okay, so there is pheromone here. So what you can expect to happen is the resident male should detect the pheromone via the VNO. TRP2 should be released by the hypothalamus. Watch what the resident male does. Fierce aggression. Doing what you'd expect under normal situations. There's an intruder in its territory, and it's going to be quite aggressive toward that intruder. So you can see how TRP2 is triggering aggressive behavior. Final scenario. Here we have our resident male, but TRP2 has been removed from its system, and there are biochemical ways of doing that. Now, here's our same intruder male, or it's probably a different one actually, but it too has been castrated with pheromone added, so it's kind of like the second scenario that we just looked at. But the big difference here is there's no TRP2 in the male. So the vomeronasal organ should in fact be activated, but nothing's going to happen in terms of the release of TRP2 in the hypothalamus. No TRP2. Pheromone, yes. No TRP2. Watch what happens. It tries to mate with this male. Sexual behavior, no aggression. When TRP2 has been removed from its system. So yeah, look what we can conclude from this. So the pheromones are mediating sexual versus aggressive behavior by triggering TRP2. So we have a normal male with TRP2, and of course if there's a female present, it will mate with her. But if there's a male present, that of course is a normal male that is releasing pheromone, then it will aggress toward it. And then if we have an altered male that doesn't have TRP2, well, if there's a female there, it's still going to mate with the female. But if there's a male there, an intruding male, there's no TRP2, and it's going to mate with that male. So you can see how this brain mechanism, this one protein, TRP2, is important in terms of regulating aggressive versus sexual behavior. And of course, normally it would be aggressive behavior directed toward another male. Now, of course, there are many other proteins in the hypothalamus that are involved in pheromones, but this is one that's hugely important in terms of aggression versus sex in rodents. Okay, this is a recent example that's caused some concern among the scientific community, and rightly so. This is interspecific, but we're still going to talk about it as a pheromone because it really is a pheromone, but it's working interspecifically. So in a way, it's more like an allomone, but we'll think of it as a pheromone. Okay, we emit pheromones, and we humans have pheromones, and that's been pretty well documented, but I'm not going to go into all of those examples because this course is primarily animal behavior, meaning non-human in this case. But we do. Now, it turns out that a majority, for whatever reason, it's probably somewhat sexist, I don't know, but the majority of rodent studies have been done by male experimenters. Go figure. I don't study rodents. But, there's a lot of female experimenters out there that study rodents. My wife used to do that when she was doing research. But nonetheless, here is what somebody discovered recently. And it turns out that this is because so many experiments have been done with male experimenters. It represents a huge confound in the literature. So people are really worried about that. So we have a male observing a rat in an open field and a female observing a rat. Two different experimenters. It turns out the rat is going to be differentially affected by whether the observer is a male or a female. And that's bad. Now you're going to have all kinds of weird results in your experiments. So here's what's going on with that. And the problem is with male experimenters, not female experimenters, which is why this is such a huge problem. So there we have a male in the same room observing this rodent in an open field. It's a rat, okay, about a half a meter away. Here's what they noticed: an increase in grimacing when that male experimenter is present. Why? Because the rodent is detecting his pheromones. And they actually developed this grimacing scale. Grimacing, especially the severe form way over there, is a sign of severe distress on the part of the rodent. That is not at all a happy rodent. So increase in grimacing. Increase in wall hugging, it's called thigmotaxis. So the rodents are less likely to go exploring out in the middle and just stay close to the walls, which is also a sign of distress. And then they looked at other stress measures, all go up when they're observed by human males in the same room as opposed to human females in that room instead of the male. Get the guy out, put a woman in, and now you don't have this effect. But when the guy's there, an increase in defecation, a sign of increased emotionality and distress. Increased body temperature, increased stress hormones. Whoa. So one other point is that female mice are more affected than this by male mice, Try that again. Female mice more affected than male mice. It affects both of them, but you get a greater effect in female mice for whatever reason. So how can you eliminate this? Well, there's different ways of eliminating it. First of all, you take male experimenters, have them watch rats, take female experimenters separately, have them watch the same rats in the same experimental situation, and see if you're getting the same results or different results. And if there's a different result, then you have something to worry about. I think the best way around this is what I would do if I studied rats, which I don't, is to just put a video camera in there and get out of the room. Don't have a human in the room at all. And then go back and watch the video, and you'll see what the rat's doing, and you've pretty much eliminated this confound. By the way, that rat is in fact thigmotaxing, starting to go out in the middle, getting a little bit bolder. Okay, so those are pheromones. There's a huge literature on pheromones. That is just a small sprinkling of the literature on pheromones in non-human organisms.